Hello, in this video, I will present the design and development of novel three-dimensional soft parallel robot. This research is accomplished by two students, Martin Garcia and Paul Pena, and the supervisors are myself, Ayse Tekes, and Dr. Amir Ali Amiri Magadan. The outline of the presentation starts with the design of a novel tendon-driven delta robot, continues with the experimental setup and data collection, and also on the third section, we will have the kinematic model, derivations, and dynamical modeling in MATLAB Simscape, and finally the presentation will end with the concluding remarks. Soft robotics has the potential to revolutionize the safe interaction of human and robotic systems due to the application of soft and compliant materials in the structure of the robot. This emerging technology has been utilized in different robotic systems, including medical, assistive, and search and rescue robots. There is an increasing demand for safe collaborative robotic systems that can work in close proximity to humans. Compliance in robotic systems can be achieved through active or passive compliance. The active compliance in the rigid robotic systems is based on the application of sensory force and torque data to control the position of the end effector. However, this method is complex, expensive, and requires a fast real-time response. Alternatively, passive compliance can be realized by integrating soft and compliance joints and links in the structure of the robot. However, the passive compliance system generally has lower accuracy and complex dynamics. Typically, soft and compliant robots have the serial and hybrid structure. In this current work, we are proposing a novel 3D soft parallel robot that has 3 degrees of freedom and can move in all X, Y, and Z directions. The initial soft robot was designed with 3 flexible links, 3D printed using thermoplastic polyurethane TPU filament, which consisted of an active soft link and a compliant 4-bar linkage connected with flexure hinges. The fin-like soft link with the strings allowed the link to deform in either direction once the string was actuated. If the string running on both sides of the soft link was pulled or actuated, thereby releasing the right string, the link deformed to the left. And likewise, once the right string was actuated and the left string was released, the soft link deformed to the right. The soft link consisted of 8 fins with a length of 110 mm and an overall width of 26 mm. The compliant 4-bar link enabled the tip of the soft link compliant 4-bar arm to move side to side without bending the soft link. The soft link and the compliant links were connected through a compliant flexure with 10 mm thickness to create relative motion between each. The initial soft delta robot consisted of flexible links, 3 servo motors with strings, a top platform, a bottom platform that houses the servo motors, and the Arduino. The soft links were 3D printed using TPU filament, and the top and the bottom platforms housing the servos were 3D printed using polylactic acid PLA filament. Also, the soft links were connected to the top platform, which was kept parallel to the bottom platform in its initial configuration. Each of the flexible links had embedded strings that were actuated by a pulley wheel connected to a servo motor. The servo motors were connected to an Arduino and can be controlled independently by the joysticks or a computer. If all the links are actuated in the same direction, then the top plate follows a straight up and down motion, while the top plate remains always parallel to the ground. Even though the top platform was lowered due to the outward deflection of the soft links, the displacement was not significant in this initial configuration, initial design. This was due to the string got loose after a couple of cycles due to the connections at the top end of the fin-like structure and the lack of tension. Also, in addition, the compliant 4-bar linkage was too stiff, preventing the required side-to-side motion. Consequently, the soft links bend side to side as opposed to bending along the direction in which the strings are actuated. To address these issues, the initial design was modified. Taking into consideration the lack of the tension in the strings as well as the flexibility and stiffness, the compliant 4-bar linkage was revised from having sharp corners to curved corners with a smaller thickness. Besides, the soft link thicknesses were increased from 10 mm to 14 mm to prevent excessive bending. Also, in order to resolve the lack of tension in the strings, a pulley wheel was designed to tighten the string to the servo motor as well as incorporating a spring attached to both springs. This allowed the servo to pull the string more effectively while adding more tension. In addition, the connection of the strings at the top ends of the soft robot was changed from a permanent connection to an adjustable connection by a bolt and a nut. The bolt and the nut wrapped by the spring cap added more tension to the string while allowing it to be adjusted if it becomes loose under actuation. After making the necessary adjustment to the soft delta robot, it was reassembled with the modified soft links and the pulley wheels. Additionally, the mechanism was controlled by programming by the motor computer instead of the joysticks. The soft delta robot experimental setup consisted of the soft delta robot, power supply, a laptop, Arduino, and an ultrasonic sensor to record the position. The soft delta robot was tested for up and down and side-to-side motion to ensure that the top plate remains parallel to the bottom platform, as well as testing the performance and behavior of the soft link. An ultrasonic sensor was used to measure the distance at which the top platform moves up and down. It was observed that the top platform, as the soft link moved outward, was displayed around 12 centimeters. Although soft robots provide more advantages compared to the rigid mechanisms, their modeling is much more complex since soft links deformations yield nonlinear equations. While the Coursera-Roth theory is used for the modeling of tendon-driven soft robots, modeling through finite element analysis is the most common method among many since it provides an accurate solution considering the material nonlinearity. In our design, each kinematic chain connecting the top plate to the support base is designed as a soft link connected to a compliant 4-bar linkage through soft joints. To develop the kinematic model of the soft robot, we assumed constant curvature for the motion of the 3D printed tendon-driven actuators. Here, in this equation, the sum of the position of the vertex of robot fixed platform and position of the soft actuators and position of the links, passive links, we set this equal to the position of the end effector plus the rotation matrix multiplied by the position of the vertex of moving platform. Our presented soft robot mechanism is kinematically constrained, and this kinematic constraint equation can be solved numerically to obtain the value of the required bending angle in the active links for a given position of the robot end effector. To demonstrate the application of the kinematic model, both vertical and circular trajectories have been simulated. While the figures on the left shows the simulation results of the kinematic model for vertical trajectory plus the required bending angles of the 3D printed soft actuators, the figures on the right depicts the simulation results for a circular trajectory plus the required bending angles of the soft actuators. The proposed design consists of 3 main parts: base, soft links, and top plate. A general flexible block was selected from the Simulink library to connect these 3 blocks. The soft arm consists of soft and compliant links. The compliant flexures also allow the links to bend and revolve depending on the actuation. Rigid transform blocks are used to position the placements of the cable, while a brick solid block is connected to the top of the general flexible block that will be used to tie the ends of the cable. To model the pulley mechanism, the belt cable end is connected to a pulley block located at the bottom of the general flexible block. The bottom pulley is located at a distance by using a rigid transform block. The rigid transform block is also connected to a revolute joint to rotate the pulley along with the cylindrical solid that must be used for the pulley wheel. The revolute joint and the cylindrical solid are also connected to a belt cable spool, which represents the pulley. A torque is also applied to the revolute joint to pull the cable. Once the simulation results are confirmed with the experimental setup, the soft links are integrated into the rest of the mechanism. 4 revolute joints are utilized to imitate the compliant flexures on each passive links. The basic idea in modeling the active soft links is to consider them as a discretized system which consists of rigid finite elements connected by spring damping elements. Each of the active soft links is composed of 4 segments connected through serial revolute cylindrical joints and then connected to the pulley. The passive soft links are also joined to the passive compliant links, thereby increasing the simulation time. To address this problem, a general flexible beam with TPU properties is replaced with a segmented link connected by revolute joints with the spring value having the same load deflection behavior as the general flexible block, as the complete SimScape model is shown in this slide. The strings are pulled as a function of time to obtain all possible configurations of the soft robot. The superiority of the SimScape modeling of soft robots is that any data can be exported if the corresponding sensors are utilized in the model. As shown in this slide, we obtained the displacement of the top plate in all dimensions. The top plate moved almost the same amount, which is around 12 cm as the prototype, validating the SimScape model. Although the simulation time will significantly be affected, as an alternative to the creation of the design using the Simulink library blocks, the CAD model of the mechanism can be imported into SimScape, and the soft links and the flexures can be replaced with the flexible beams and torsional springs. The compliant 4-bar linkage can also be modeled using pseudo-rigid body modeling by replacing each flexure with their equivalent torsional stiffness having the same load deflection behavior. This research study presents the design, modeling, and development of a novel 3D soft parallel robot that is analogous to a rigid delta robot. The robot consists of 3 closed kinematic chains that connect the top platform to the bottom platform through soft links and joints. The robot structure was 3D printed using TPU and actuated through 3 tendon-driven soft links. The kinematics model of the robot is derived based on the constant curvature assumption, and the simulation results show that the robot can move in 3-dimensional trajectories. The dynamics of the soft robot is simulated using SimScape. To emulate the motion of the soft links, they have been modeled using discrete sets of elements connected using rotary joints and springs. The comparison of the experimental data and simulation results indicates the effectiveness of the SimScape model.